Hello guys, welcome back to my channel Gamma Di Gamma. And in this video I would actually like to continue my high school calculus playlist. So last time, talking about high school calculus playlist again, I left off at derivatives 4, which basically involved the category variable raised to variable. And now we'll be doing something that's pretty new from a high school standpoint. That's basically tackling parametric forms in differential calculus, or calculating the derivatives of parameterized functions. So let's get started. Okay, so before actually going into the calculus of stuff, let's try to understand what parameterization is or what parametric forms are. So first of all, let's actually consider a regular function. And when I say a regular function, and we start talking about the graphical representation of a function, what comes into mind is actually something like this. So call this the x-axis, and this is y is equal to f of x. Y is a function of x. Say something like this, a curve. Yeah, this can be a function, definitely. Say that extends till infinity. Anyways, so this is what may come into mind at first. And if you want to name this point, call it a given point is some x, some horizontal distance x, and some vertical distance y. But y is f of x, so any point can be represented as collection of x and f of x. That's why any curve is a collection, infinite collection actually, of points. There are infinite number of points on a curve, and this is seems pretty clear when we write any point on this curve as x comma f of x. X comma f of x is a point, and this point is changing, this point is varying. That's why it's called a variable anyways, but it's a varying point. So the position of this point changes for every choice of x that we have. And this is actually the traditional way of looking at functions. That's why call this the independent variable. And f of x or y the dependent variable, because it clearly depends on x. It's a function of x. That's why in a conventional sense we used to differentiate with respect to the independent variable, which was in most cases x, unless you called it something else. But um, and the typical characteristic of the independent variable is it is regular in the sense that it goes from say 1 2 3. I mean, there are values it can take between 1 and 2, like fractional values, infinite fractions between 1 and 2, but I'm not going to write them down. So the independent variable x goes or moves, if you want to think about it that way, with a uniform rate. That's why the derivative of x with respect to itself is 1, because think of the derivative as a rate measurer. Then the rate at which x changes with respect to itself is 1, right? Because as I said, x is going with a uniform rate. And then we compare f of x, or whatever is the dependent variable with respect to this uniform x, right? That was our entire basis of differentiation up till now. But now we're going to do things slightly differently. So now what we're going to do is we are going to work the other way around. So here we had a function and then that function traced a curve graphically. Here we have a curve and we actually want to represent this in terms of some variables. So what we're going to do now is have any point, call this point P, and define that to be, say, g of t comma h of t. And how that is helpful is because instead of x that we had, instead of having a point, these dynamic points as independent variable comma dependent variable, we are writing them as variable comma variable, but both of them are functions of t. Both of them are functions of t. So both of them are dependent variables because they both depend on t. Both of them are functions of t. So we are defining a new unique independent variable. And you may say, I mean, how is that helping us? Because originally we had an x, we just replaced an x with a t. But the thing is, here on this graph, we relied on the mercy of x. I mean, x, went from all negative real numbers to all positive real numbers, right? Here we can actually specify what is the starting point. T starts from what number and ends at what number, because notice this curve goes from a prime to b prime, so we can have certain values, say 0 for t, and then some final value t sub f for the final value. We can let t range from these values. So this is what we can define, what users or people who want to parameterize can define. Here we are relying on the mercy of all real numbers, and that's why this curve is going to infinity. But what if we don't want a curve? What if we want to define a path, this curved path, for more practical considerations, right? If you're like, say, an engineer, you want to have information about a path, say you want to fence this thing, then it's wise to use parameterizations of this sort and solve the problem. So now we are having two dependent variables, functions of t, and whatever function you have for g does not affect whatever function you have for h. So say if you have x squared, or say t squared in place of g, and you have t cubed in place of h, I mean, the fact that g is t squared does not affect the fact that h is, well, t cubed. But if you want to think about the bigger picture here, you might call this a vector. And vectors traditionally are shown with arrows, so you would have to use arrows to represent this. So g represents how many steps you take vertically, and h represents how many steps you take vertically, and g represents how many steps you take horizontally. So any point P is a collection of some vertical steps and some horizontal steps. But if in the situation that you want to call this a vector, then you let this axis be the t axis and this axis be the x bar of t axis, or the position vector of t axis, which is defined as basically g of t comma h of t. And this is a vector because it has two components, the g component and the h component. And I'm gonna probably make a video on vectors real soon, when it comes to physics. But this is, what this parameterization enables us to do. It makes us see a greater picture. And if you want to uh, compare this and our conventional stuff, if you let g of t equal t and keep h of t as it is, you get this conventional picture. I mean, you can have parameterizations like this. Say if you want to parameterize a parabola, you would have t comma t squared as the parameterization. But I mean, I'm making a video on how to parameterize separately. But trust me, this is really useful when it comes to projectile motion, because without parameterizations and vectors in general, and how your one component does not affect the other component, without this fact, projectile motion or even vector calculation of two-dimensional space would not have been possible. So this is really powerful, and please, I hope you understand this concept, because we're going to need this later for line integrals and their higher forms, or surface integrals. And this is basically the greatest tool any engineer can have in his pocket, his or her pocket. So that's all about parameterization. I will make another video on it, mind you. So stay tuned for that. Okay, so that was a brief glimpse of what parameterizations were. Now let's stick to what we have to do in a differential calculus with these parametric forms. So let's do some examples. So we have to find dy over dx in all the examples I do on this page. So first, they've given us y is equal to 8 times t to the fourth, and x is equal to 280 squared. So just to put things into perspective with regards to the last page where I explained the parameterizations, this will be a curve, some curve, I don't know what shape it has, going from some initial t naught value to some final t final value. And again, they haven't told us what t is. So we don't need to write this, but let's just say t goes from t naught to tf. That's basically the length of this entire curve. And any point on the curve, call it q, can be represented as x comma y, and x is 2at squared comma at to the fourth. But still, if you want to label the axes, call this the t-axis and call this the x comma y axis, or if you want to write this as a vector, x bar axis. And this is helpful because now y does not depend on x, but both of them depend on a new independent variable t. So this t is the new independent variable. So we can actually have different behaviors for x and y. X does not need to be uniform now. X does not need to have a uniform rate of 1 2 3 4. X has a different rate, but when we talk about rates, we have to talk about comparison with respect to what? T. X has a distinct rate with respect to t, which can be given as dx over dt, and y has a distinct rate which is given by dy over dt. But now the independent variable is t, so t has a uniform rate with respect to itself, naturally, because that's the only independent variable. So you would want to differentiate with respect to t. But look what they're telling us to find. They're telling us to find dy over dx, and you're like, this is pretty counterintuitive with regards to what we just learned, that x does not depend on y, does not depend on x. So how are we going to do this? So looking at each of these, as I said, we can differentiate with respect to the independent variable t. That's the logical thing to do. So this means we can find dy over dt, and we can find dx over dt. So what I'm going to do is say dy over dx is equal to dy over dt, all divided by dx over dt. And this, you may say, is, you can say that the dt's cancel out, but the way I like to think about this is, remember you had your chain rule, say derivative with respect to x of f of g of x, so a composite function like this was basically derivative of f of g of x with respect to g of x times derivative of g of x with respect to x. So it's almost like these derivative of g of x were cancelling out, and we basically had this initial expression. That's why we obtain f prime of g of x times g prime of x. So, if we can cancel the differentials over multiplication, we can definitely cancel them out over division. So that's how I like to think about it. So now let's calculate each of these individually. So we can calculate dy over dx. So dy over dt, my bad. I'm still in that conventional zone. So dy over dt is simple. It's 4a t cubed, and we can calculate dx over dt. That's going to be 4 at, and then divide both of them. So dy over dx first, 4a t cubed over 4at. 4's and the a's cancel out. We have t cubed over t, which is nothing but t squared. So basically the dy over dx, or you can say that the tangent line at that point, at that t, actually depends on the value of t. So at t equals to, the tangent line has a slope of t squared, or 4. So assuming, this is like the tangent line, this has a slope of 4, or t squared rather, more generally. Let's do another example. Okay, example 2. We have parameterizations. X is equal to a times cosine theta and y is equal to a times sine theta. And if you want some more perspective, this parameterization results in actually a circle of radius a. So any point G can be expressed as a cosine theta and a sine theta, and for a circle, theta should go from 0 to 2 pi if you are talking about principal angles, but we can have 4 pi, or so basically the rotation goes on, and anti-clockwise sense, because angles are measured in anti-clockwise sense. So this basically traces out a circle of radius a, and again you can you can call this theta, and you can call this x bar, or x comma y vector, if you want to put it that way. If you call it a vector, then make an arrow, or just let it be. Just call it a parameterization, and just call it a dynamic point that varies with theta. Parameterizations are, in a nutshell, dynamic points. So anyways, it traces out a circle of radius a. So again, we have to find dy over dx, and we can use a strategy that we used before, dy over d theta divided by dx over d theta. So let's find dy over d theta. It's simple. It's going to be a times cosine theta. Dx over d theta is negative a times sine theta, and then this ratio then becomes a times cosine theta over negative a times sine theta. A's will cancel out. We have negative cosine theta divided by sine theta that will become negative cotangent of theta. I mean, if all the trigonometric relations identities were derived from the unit circle, here we just have a circle of radius a, but still the tangent to this point is related to the tangent function. Here it's the cotangent because of the parameterization we had. So yeah, that's it for example 2. Example 3 now. Fair enough. Oh, okay, we have example number 3. So we have parameterizations. X is equal to 2 times bt over 1 plus t squared, and y is equal to a times 1 minus t squared over 1 plus t squared. So they're telling us to find dy over dx, but at t equals 2. And although you may say, conventionally we had the dy over dx being a function of x, but since everything is parameterized with t here, this will be a function of t. That's why you have to plug in t equals 2 later on. So again, we do as we've always done, dy over dt divided by dx over dt, but all of this evaluated by at t equals 2. So let's find dy over dt. So dy over dt is derivative with respect to t of 8 times 1 minus t squared over 1 plus t squared. And it looks like we're going to have to use the quotient rule of differentiation. So a is a constant times 1 plus t squared as it is. Derivative of the inside is negative 2t minus a as it is, 1 minus t squared as it is, and the derivative of the denominator is 2t divided by the denominator squared, or 1 plus t squared, the whole thing squared. And if you were to simplify stuff, if negative 280, just multiply minus 280 squared minus 280 plus 280 squared over 1 plus t squared squared. And these quadratic t terms cancel out, giving us just negative 480 divided by 1 plus t squared squared. Now dx over dt is just going to be d over dt of 2bt over 1 plus t squared. Again, quotient rule because of the t in the numerator. So we just have 2b outside, 1 plus t squared, derivative of t is 1, minus 2bt times derivative of the denominator is 2t over 1 plus t squared squared, just like this. And then we obtain 2b plus 2b t squared minus 4b t squared over 1 plus t squared squared, which simplifies to 2b minus 2b t squared over 1 plus t squared squared. So then again, dy over dx was dy over dt over dx over dt. So that now is going to be this negative 480 over 1 plus t squared squared, and then dividing is multiplying by the reciprocal. So 1 plus t squared squared over 2b minus 2b t squared. So these things cancel out. We can take the negative, flip the order, and divide by a 2. So we have 280 divided by bt squared minus b, but we need to find dy over dx at t equals 2. So plug in t equals 2 in here. We have 4a over um, 4b minus b or 3b. That's basically our answer for this. Okay, so now in the later half, we're going to actually be introduced to a slightly different idea. So now they're telling us to differentiate with respect to x cubed the function sine of x squared. And you may say this is just utter nonsense going on now. But think about it in the think about it in terms of parameters. So assuming you have a graph, a curve, and then any point, call it b, can be expressed as a function of or rather collection of x cubed comma sine of x squared, where x is the independent variable. You could have taken t. I mean, it doesn't matter um, what this variable is. X is the independent variable, and the call, you can say this is a vector or a dynamic parameterized function or a dynamic point that's moving around to trace out this curve of, say, x bar of small x cubed comma sine of x squared. So it's basically parameterization. So it's, if you again say, if again change of variables just quickly, call x, instead of x you call it t, so t cubed and sine of t squared. What they're telling us to find then over here is differentiating with respect to t cubed of sine of t squared. And if you say call this y and call this x, this our problem just becomes dy over finding dy over dx. So that's why when they tell us to find, now forget this change of variables, let's treat stuff in x's. So when they tell us to differentiate with respect to x cubed, what they're telling us to do is find d of sine of x squared, differentiate that with respect to x cubed like this. But using the logic of differentiating parameterized functions, we differentiate the numerator with respect to the independent variable, which in this case coincidentally happens to be x, and then divide that by the derivative of the denominator, basis of differentiation. We call it whatever it was in the basis, call it the basis of differentiation, because that's what we were differentiating with respect to. So have that variable again differentiated with respect to its independent variable, and since both of them have same independent variables as do most all parameterized functions, that's why the dx's will cancel out. You can think about it that. So this is basically the treatment of parameterized functions that we did on the previous page, and doing this is easy. So this will become cosine of x squared multiplied with 2x divided by 3x squared. So one of the x's will cancel out. We have 2 over 3 times cosine of x squared divided by x. That's basically what we needed to find. Okay, so let me do some few more examples with such kind of language, just to drive home the point. So example number 2 goes like this. So they're telling us to differentiate sine inverse of 2x over 1 plus x squared with respect to cosine inverse of 1 minus x squared over 1 plus x squared. And just for our convenience of writing stuff, call the first function f and call the second function g. So what they're telling us to find is basically df over dg. And since again the independent variable is x, we can use the same treatment of parameterized functions that we did previously to write this in this way. Okay, so for that we need derivative of f with respect to x and derivative of g with respect to x. So first, let's look at f. F is sine inverse of 2x over 1 plus x squared. I mean, I don't know how many of you realize this, but inverse functions and standard forms inside them, as arguments of these inverse trigonometric functions, actually scream out to us that we could potentially simplify using trigonometric substitution. So take x to be tan theta. I mean, if you don't know why I did this, just check out my derivatives, one of my derivatives video, where I covered this trigonometric derivative by substitution category. So when I do that, we have sine inverse of 2 times tan theta over 1 plus tan squared theta. And there's a direct formula. This is the sine double angle formula in terms of tangents, but let's just simplify it conventional way. So this becomes 2 tan theta over 1 plus tan squared theta is secant squared theta. And now write everything in terms of sines and cosines. So tan is sine theta over cosine theta, and then this secant is 1 over cosine squared theta, which is cosine squared theta in the numerator. So one of the cosines cancel out. We have sine inverse of 2 times sine theta cosine theta, and this 2 times sine theta cosine theta is sine of 2 theta, the double angle formula of the sine. So then sine inverse and sine cancel out, giving us 2 theta. F is 2 theta, and theta, taking inverse tangent on both sides, is inverse tangent of x. So we just have 2 times inverse tangent of x on our hands. So df over dx is simply 2 times derivative of inverse tangent of x with respect to x. That is going to be 2 over 1 plus x squared. Simple as that. Okay, that was for df over dx. That was for the numerator. Now let's take a close look at g. G happens to be cosine inverse of 1 minus x squared over 1 plus x squared. And now again, looking at the denominator and the inverse trigonometric function outside, again it's crying for trigonometric substitution. So let's take x to be tan theta. Now we have cosine inverse of 1 minus tan squared theta over 1 plus tan squared theta. And if you want to write this in terms of sines and cosines, this is going to be 1 minus sine squared theta over cosine squared theta divided by 1 plus sine squared theta over cosine squared theta. Taking the common denominator and cancelling out the cosine squared that are common. So cosine squared theta minus sine squared theta over cosine squared theta plus sine squared theta. Great fact, the denominator cosine squared theta plus sine squared theta goes to 1. So we just have cosine inverse of cosine squared theta minus sine squared theta, which, if you know your double angles, is cosine of 2 theta, the double angle formula for the cosine. This just turns out to be 2 theta, and theta is inverse tangent of x, that is g. So dg over dx is 2 times derivative with respect to x of inverse tangent of x. So we just have 2 over 1 plus x squared. Fair enough. Now take the ratio of both of them. So df over dg that we intended to find was df over dx divided by dg over dx, and since both of them This turned out to be 2 over 1 plus x squared. Terms cancel out and we have 1 as the intended answer for this df over dg. Isn't that fascinating? I mean, two um, two separate functions that only depend on x, which is the independent variable, but once you take the derivative with respect to of one function with respect to the other, you just end up with 1. So it's like sine inverse of 2x over 1 plus x squared. F is um, on if you were to graph something like cosine inverse of 1 minus x squared over 1 plus x squared on the x-axis here, and on the y-axis, say if you were to graph sine inverse of 2x over 1 plus x squared, then it would trace out a straight line like this, like the graph y equals x, which has again itself a derivative of 1 with respect to x. Instead of that x, we have this cosine inverse function. Isn't that really fascinating? You could try this with a graphing calculator. It'll help. Okay, so another example now. Here, it's the question framed is really weird. So we have to prove that derivative of inverse tangent of x over 1 plus square root of 1 minus x squared with respect to sine inverse of x is independent of x. So that means if you call this function f, call this function g, df over dg basically will be some value and it does not contain x. It doesn't contain x. Otherwise it would be dependent on x. Without x, it's independent of x. Like that. So again, df over dg, use the similar strategy, df over dx divided by dg over dx. So df over dx first. Df over dx is derivative with respect to x of inverse tangent of x over 1 plus square root of 1 minus x squared. I mean, I know we can do this by trigonometric substitution, but just for the sake of old times, let's do it with the classical way. So we have to use the chain rule first for the inverse tangent, and then to calculate the derivative of the inside part, the argument of the inverse tangent, we need to use the quotient rule. So it's going to be a big one. Don't worry. So we have 1 plus argument squared x squared over 1 plus square root of 1 minus x squared whole thing squared times the derivative of this inner part. So for that we have to use the quotient rule. So keeping the denominator as it is, 1 plus square root of 1 minus x squared, you differentiate x, which just turns out to be 1, minus, then have x as it is, then differentiate this inner part with respect to x, which I'm skipping a lot of steps, is negative x over square root of 1 minus x squared, because the 2's will cancel out, over the denominator squared, which is 1 plus square root of 1 minus x squared whole thing squared. That's basically the derivative. We can simplify stuff. So taking the LCM here, 1 plus square root of 1 minus x squared on top, squared like this, and then we basically have this quantity 1 plus square root of 1 minus x squared, the whole thing squared, plus x squared multiplied with 1 plus square root of 1 minus x squared plus x squared divided by square root of 1 minus x squared all over 1 plus square root of 1 minus x squared, the whole thing squared. Now the nice part is these nasty terms will cancel out. So we are left with 1 over, square this, 1 plus 2 times square root of 1 minus x squared plus this thing squared is 1 minus x squared plus x squared. You can do the same thing over here. We have square root of 1 minus x squared like this, and then square root of 1 minus x squared times square root of 1 minus x squared is 1 minus x squared plus x squared divided by square root of 1 minus x squared. So the x squares will cancel out. So 1 plus 1, 2. 1 over 2's can be factored out. 1 plus square root of 1 minus x squared like this. X squares cancel out. We have 1 plus square root of 1 minus x squared like this divided by square root of 1 minus x squared. And notice that these terms cancel out. So our df over dx just turns out to be half times square root of 1 over square root of 1 minus x squared. Okay, now g. So dg over dx was a derivative with respect to x of inverse sine of x. And this is a standard form. It's 1 over square root of 1 minus x squared. So now df over dg is the first divided by the second. So 1 over 2 times 1 over square root of 1 minus x squared times 1 over this is square root of 1 minus x squared. Stuff cancels out. We have half, which is a constant and does not contain x, is independent of x or any other variable, hence proved. Whatever we had to prove. Yeah, that's it. Now one final example to actually tie in the entire concept that we learned in the last derivatives 4 video, which was variable raised to variable. So we are going to implement that. So we have to differentiate x to the x. So you see variable to the variable with respect to x times the natural log of x. So what you do is you call the first function f, call the second y. We need to find basically df over dg, which is going to be df over dx divided by dg over dx. So we need to find df over dx, and we have variable raised to variable. So remember what we did in the entire derivatives 4 video. We took the natural log to get the power down. So f is x to the x. Take natural log on both sides. Natural log of f is equal to natural log of x to the power x. Using properties of natural log, this is going to be x times natural log of x. Now you differentiate both sides, and for this we need to use the concept of implicit differentiation. Check that video out if you haven't already. This is going to be 1 over f times df over dx is basically equal to x times the derivative of natural log of x plus natural log of x times derivative with respect to x of x. Product rule basically. So df over dx is f times all this junk. F is x to the x. X to the x times x times derivative of natural log of x is 1 over x plus this will become 1. We just have natural log of x. this goes down to 1. So we have df over dx to be x to the x times 1 plus natural log of x. Fair enough. And now time for g. So g is x times natural log of x. And no fuss in differentiating this. So dg over dx is going to be d over dx of x times natural log of x. Use the product rule, x times derivative with respect to x of natural log of x plus natural log of x times the derivative with respect to x of x. We have x over x plus natural log of x times 1, which will be 1 plus natural log of x. So df over dg, according to the formula over here, is going to be x to the x times 1 plus natural log of x divided by 1 plus natural log of x, and these cancel, so it's just x to the x. So which means if you were to graph um, f versus g, for example, with x to be an independent variable, a parameter ranging from some value to some final value, you would have some curve which would have slope of x to the x, or an exponential slope, exponentially increasing slope at any choice of parameter x because of x to the x. Isn't that really nice? You can graph this up again. I'm sure this graph will have a will increase like crazy. So that's pretty much the concept of differentiation of parametric forms that is required at a high school level, I think. Hope you learned a lot in this video. So please like, share, and subscribe to my channel. Recommend me to your friends, people who are struggling with high school calculus or need to learn on their own during this lockdown period. You can follow me on Instagram, gamma underscore digamma. And in the meantime, stay home, stay safe, and have a great day. Peace out.